In this lecture, we're going to continue talking about adding constraints to integer or linear programs. We're also going to introduce the idea of a separation problem. We'll explain what a separation problem is and why we're going to need it. Before we introduce these things, let's first revisit the cutting plane algorithm. Our standard example is going to be the classic integer program that we've been looking at. We're going to be maximizing a function, f of x, subject to a set of linear constraints that define some polyhedron p. And we're going to intersect this polyhedron p with the integer lattice. Intersecting this polyhedron with the integer lattice creates our feasible space x. Here we have a graphic of exactly what this polyhedron p is. The polyhedron p is in pink, and the feasible region are the blue dots. In the cutting plane algorithm, in addition to this integer program, we also need a set of valid constraints. Throughout these lectures, we're going to call capital C our set of valid constraints. Recall that a set of valid constraints doesn't mean that they're all useful. Here we have pictured some valid constraints for this feasible region X. Note that all of these constraints are valid because they don't exclude any points from the feasible region. That is, all the feasible points X that are feasible are on the proper side of these inequalities. There is, however, one constraint that, although valid, could potentially be not very useful. This constraint out here actually doesn't create any useful constraint because it doesn't cut off any solutions from P. In the cutting plane procedure, we iteratively add valid constraints into our polyhedron. We do this by first solving and finding the optimal solution in our polyhedron. We call this x star. After we find x star, we find some constraint that is violated by this particular solution. We find this constraint that's violated, and we add it to our polyhedron and iterate. This middle step, finding the constraint that's violated by our particular solution, is called the separation problem, and we're going to focus on it quite a bit in these lectures. Although the cutting plane algorithm is going to be our inspiration, it's not really going to be what we're focused on. We're going to be focused on something more general. We'd like to have some procedure that allows us to use inequalities. And in general, this is going to have two ingredients. We first have to characterize our set of inequalities. We have to find our set C. And then, given some solution x star, we have to be able to find some violated constraint inside of our collection. This is the separation problem. We'll define the separation problem formally in just the next slide. Here we can just get an idea. We're going to be given some solution x star, and given this solution, we're going to find some constraint inside of our collection that's going to be violated. We've seen a valid collection of constraints before. The Chantal-Garmery cuts form a collection of constraints, and in fact, all constraints fall inside of this collection. We also saw how to use these cuts inside of a cutting plane algorithm. This wasn't exactly a separation problem, but it was quite close. In this case, if we have some x star that's a basic feasible solution for our linear program, then we can find a violated cut. Unfortunately, this isn't the separation problem in general because this is restricted to only basic feasible solutions of our linear program. If we were given a non-basic feasible solution, we wouldn't be able to find a violated cut, at least with our current procedure. Throughout these lectures, what we're going to do is continuously introduce new sets of valid inequalities and then identify the separation problem and solve it. To be more precise about the separation problem, we can formulate it with an explicit input and an explicit output. The input to the separation problem is the set of feasible points x, a polyhedron P, some solution x star inside of P, and some collection of inequalities. The separation problem is always defined with respect to a particular set of inequalities, capital C. Usually this x star is going to be some optimal solution with respect to an objective function, but that's not necessary. The output of the separation problem is some particular constraint inside of our collection so that this constraint is violated by x star. Alternatively, if we don't find some constraint that's violated, then we have some guarantee that this solution x star actually lands inside of our initial feasible points, capital X. In general, though, we're going to assume that our x star isn't a feasible solution for x, but is only a feasible solution for P, our polyhedron.